Welcome back to another Sleepy Steve story. Before we drift off tonight, remember to subscribe to help Steve-O out, and I will keep making more sleepy stories to help you study gently, revise quietly, and settle your mind at the end of the day. Tonight, we are staying in Unit 3 Chemistry, Area of Study 1, and we are continuing to think about energy. In the last episode, we looked at fuels, combustion, and energy options. We thought about fossil fuels, biofuels, complete combustion, incomplete combustion, carbon dioxide, energy supply, and the way different fuels can be compared. Now we are going to slow the idea down even further. Instead of only asking which fuel is used, we are going to ask how much energy is released, how that energy can be measured, and how chemists communicate energy changes in chemical equations. This episode is about thermochemistry, enthalpy, and calorimetry. You might picture a quiet chemistry laboratory late in the afternoon. The benches are clean. The Bunsen burners are turned off. A copper calorimeter sits quietly on a heat-proof mat. A thermometer rests inside a small beaker of water. A spirit burner waits beside it, with its lid still on. Nearby, a student has drawn a simple energy profile on a page with reactants on one side, products on the other, and a small arrow showing whether energy is released or absorbed. The room is calm. Nothing is rushing. There is only the quiet idea that chemical reactions are not just rearrangements of atoms. They are also exchanges of energy. Some reactions release energy to the surroundings. Some reactions absorb energy from the surroundings. And in VCE chemistry, we need to describe, calculate, and evaluate those energy changes carefully. So take a slow breath in and a slow breath out. Let the laboratory settle around you. And let's begin with the word thermochemistry. Thermochemistry is the study of energy changes in chemical reactions. It asks how much heat energy is transferred when bonds are broken and formed, when fuels burn, when substances dissolve, or when reactions occur in a measured system. The key idea is that chemical reactions involve changes in chemical potential energy. Reactants contain energy in the bonds and interactions between particles. Products also contain energy in their bonds and interactions. If the products have less chemical energy than the reactants, the extra energy is released to the surroundings. This is an exothermic reaction. The surroundings become warmer because energy has moved out of the reacting chemicals. Combustion is a common example. When methane burns in oxygen, carbon dioxide and water are formed, and energy is released. When petrol burns in a car engine, energy is released. When ethanol burns in a spirit burner, energy is released. An exothermic reaction has a negative enthalpy change. You will often see this written as delta H is less than 0. Delta H simply means the enthalpy change for the reaction. In a sleepy way, you can imagine the reactants sitting higher on an energy hill and the products settling lower down. As the reaction moves from higher chemical energy to lower chemical energy, energy flows out into the surroundings. The reaction gives warmth away. If the products have more chemical energy than the reactants, energy must be absorbed from the surroundings. This is an endothermic reaction. The surroundings may become cooler because energy is taken in by the reacting system. An endothermic reaction has a positive enthalpy change. Delta H is greater than 0. You might imagine the product sitting higher on the energy hill than the reactants. The reaction needs energy to climb. In Unit 3 Chemistry, we use these ideas to interpret thermochemical equations. A thermochemical equation is a balanced chemical equation that includes the enthalpy change. It does not only tell us what reacts and what forms, it tells us the energy change associated with the mole quantities shown in the equation. For example, the combustion of methane can be represented by a balanced equation. Methane reacts with oxygen to produce carbon dioxide and water. When the equation includes the enthalpy change, it tells us how much energy is released for the amount of methane shown. The important exam idea is that the enthalpy change belongs to the balanced equation as written. If the equation shows 1 mole of methane combusting, then the enthalpy change refers to 1 mole of methane. If we double the equation, we double the enthalpy change. If we reverse the equation, the sign of delta H changes. So thermochemical equations are not just symbols. They are measured energy statements. They are like a quiet receipt for a chemical reaction, showing both the substances and the energy transferred. Now let's pause on enthalpy. In VCE chemistry, enthalpy is often treated as the heat content of a system at constant pressure. We usually focus on the change in enthalpy rather than trying to measure total enthalpy directly. The enthalpy change is the difference between the energy of the products and the energy of the reactants. If energy is released, delta H is negative. If energy is absorbed, delta H is positive. For combustion reactions, we often refer to the enthalpy change as the heat of combustion. The heat of combustion is the energy released when a specified amount of fuel undergoes complete combustion. It can be expressed in different ways depending on the context. Sometimes we use kilojoules per mole, which tells us the energy released per mole of fuel. Sometimes we use kilojoules per gram, which helps compare fuels by mass. Sometimes we use kilojoules per liter, which helps compare liquid fuels by volume. In exam questions, students need to watch the units carefully. A fuel that releases more energy per mole may not always be the best fuel by mass, by volume, by cost, by availability, or by environmental impact. Chemistry often asks us to compare, not just calculate. So a strong answer might say that a fuel with a high heat of combustion is energy-rich, but the evaluation should also consider carbon dioxide emissions, renewability, storage, transport, toxicity, and practicality. Now let's move to calorimetry. Calorimetry is the experimental measurement of heat energy changes. A calorimeter is a device used to measure energy transferred as heat. In school chemistry, calorimetry can be as simple as a spirit burner heating a known mass of water in a small container. It can also involve more controlled equipment, such as a solution calorimeter or bomb calorimeter, depending on the reaction being studied. The central idea is gentle and simple. If a reaction releases heat, that heat can warm another substance. If we know how much the substance warms, and we know its mass and specific heat capacity, we can calculate the energy transferred. For water, the useful relationship is energy equals mass times specific heat capacity times temperature change. In symbols, Q equals mc delta T. Q is the energy transferred, usually in joules. M is the mass, usually in grams. C is the specific heat capacity, often 4.18 joules per gram per degree Celsius for water. Delta T is the change in temperature. This equation is one of the quiet anchors of thermochemistry. It tells us that the energy absorbed by water depends on how much water there is, how hard it is to heat, and how much its temperature changes. A small amount of water warming a lot may absorb a similar amount of energy to a larger amount of water warming only a little. The equation helps us measure the difference carefully. Now imagine the spirit burner again. A student records the initial mass of the burner and fuel. They measure a known mass of water in a beaker or calorimeter. They record the initial temperature of the water. They light the fuel, gently heating the water. After a short time, they extinguish the flame and record the final temperature. They also measure the final mass of the burner and fuel. From this, they can calculate the mass of fuel burned. They can calculate the temperature rise of the water. Then they can calculate the energy absorbed by the water using Q equals mc delta T. If they want energy per gram, they divide the energy absorbed by the mass of fuel burned. If they want energy per mole, they use the molar mass to convert the mass of fuel into moles, and then divide the energy by the number of moles burned. This is where thermochemistry connects with earlier chemistry learning. Moles matter again. Mass matters again. Balanced equations matter again. Units matter again. A calm calculation might move in this order. First, find the temperature change. Second, calculate the energy absorbed by the water. Third, find the mass of fuel burned. Fourth, convert the mass of fuel to moles if required. Fifth, calculate the energy released per gram or per mole. Sixth, remember that combustion is exothermic, so the enthalpy change is negative if written as energy released by the reaction. The arithmetic may feel busy, but the story underneath is simple. Fuel burns, water warms, the temperature rise is measured, the energy transfer is calculated, the fuel is compared. Now we need to be careful. In a simple school calorimetry experiment, not all the energy released by the fuel is absorbed by the water. Some energy is lost to the air. Some is absorbed by the beaker or calorimeter. Some may heat the thermometer. Some may be lost because the flame is not perfectly positioned. Some may be lost because the fuel does not burn completely. Some may be lost because water evaporates. This means the experimental value for heat of combustion is often lower than the accepted value. The fuel releases more energy than the water appears to absorb. The water only catches part of the energy. So, in evaluation questions, students should not simply say human error. That is usually too vague. A better response identifies a specific source of error and explains its effect on the calculated result. For example, if heat is lost to the surroundings, the measured temperature rise of the water is lower than it should be, so the calculated energy absorbed by the water is too low, and the calculated heat of combustion is lower than the accepted value. That is the kind of linked explanation that exam responses reward. Let's consider incomplete combustion. If a fuel burns with limited oxygen, it may produce carbon monoxide or carbon instead of only carbon dioxide and water. Incomplete combustion releases less energy than complete combustion. It also creates harmful products. Carbon monoxide is toxic because it binds strongly to hemoglobin and reduces oxygen transport in the blood. Soot or carbon particles can contribute to air pollution. So when we discuss energy efficiency and fuel choice, incomplete combustion matters. It affects energy output, safety, and environmental impact. Now let's think about solution calorimetry. Not all calorimetry involves burning a fuel. Some experiments measure temperature changes when substances dissolve or when aqueous solutions react. For example, an acid and base may react in a neutralization reaction, releasing heat. A salt may dissolve in water and cause the temperature to rise or fall. Two solutions may be mixed, and the temperature change of the solution can be measured. In these cases, the solution is often treated as if it has the same density and specific heat capacity as water, unless the question gives other values. The same equation can still be used. Q equals mc delta T. But now the mass may be the mass of the solution, not just the water. If two solutions are mixed, students may need to add the volumes together and use density to estimate the total mass. Again, the story is simple beneath the details. A chemical process occurs. The solution changes temperature. The energy transfer is calculated. Then the result is connected back to the reaction. Some calorimeters use a calibration factor. The calibration factor is the energy required to increase the temperature of the calorimeter by 1 degree Celsius. It is often given in joules per degree Celsius. If a calorimeter has a calibration factor, energy can be calculated using Q equals calibration factor times temperature change. This matters because a real calorimeter absorbs heat too. The calibration factor accounts for the whole calorimeter system, not just the water. In a more controlled experiment, calibration improves accuracy because it recognizes that the equipment itself is part of the energy transfer. So, students should look carefully at what the question gives them. If the question gives mass, specific heat capacity, and temperature change, use Q equals mc delta T. If the question gives a calibration factor and temperature change, use Q equals calibration factor times delta T. Do not mix the two approaches unless the question clearly asks you to. Now, let's return to energy profiles. Energy profile diagrams help us visualize enthalpy change. For an exothermic reaction, the reactants are shown at a higher energy level than the products. The arrow from reactants to products points downward, and delta H is negative. For an endothermic reaction, the reactants are shown at a lower energy level than the products. The arrow points upward and delta H is positive. Energy profiles can also show activation energy. Activation energy is the minimum energy required for particles to react when they collide. Even exothermic reactions need activation energy to begin. A match must be struck. A spark must ignite the fuel. The reaction may then release much more energy than was needed to start it. This helps explain why fuels do not all burst into flame just because they contain chemical energy. There is energy stored, but a barrier must be overcome. Later, when students study reaction rates, activation energy becomes even more important. But in this episode, it is enough to notice that energy changes and reaction pathways can be represented visually. Now, let's think about bond energy carefully and calmly. During a chemical reaction, bonds in reactants are broken and new bonds in products are formed. Breaking bonds requires energy. Forming bonds releases energy. If more energy is released when new bonds form than is required to break old bonds, the overall reaction is exothermic. If more energy is required to break bonds than is released when new bonds form, the overall reaction is endothermic. This helps explain why combustion reactions release energy. The bonds formed in carbon dioxide and water are very stable. A lot of energy is released when those product bonds form. The overall reaction releases energy to the surroundings. In an exam, students may need to connect bond breaking and bond forming to the sign of delta H. A strong explanation might say that bond breaking is endothermic, bond forming is exothermic, and the overall enthalpy change depends on the difference between energy absorbed and energy released. Now let's bring the ideas together with an example. Imagine a student comparing ethanol and propan-1-ol as fuels. They burn each fuel separately under the same mass of water. They record the temperature rise. They calculate energy absorbed by the water. They calculate energy released per gram of fuel. They may find that one fuel produces a larger temperature rise for the same mass burned. But a good evaluation does not stop there. It considers whether both fuels burned completely. It considers whether the same distance was kept between flame and beaker. It considers heat loss to the surroundings. It considers whether the wick length changed. It considers whether there was soot on the container. It considers whether the lid was used. It considers the uncertainty in temperature readings and mass measurements. And then it makes a reasoned conclusion. This is the difference between simply doing a calculation and doing chemistry. Chemistry uses data. Chemistry questions the data. Chemistry explains what the data can and cannot show. Now let's think about accuracy, precision, reliability, and validity. Accuracy refers to how close a measurement or result is to the true or accepted value. If a calculated heat of combustion is close to the databook value, it is more accurate. Precision refers to how close repeated measurements are to each other. If repeated trials produce very similar results, the data is precise. Reliability is improved by repeating trials and obtaining consistent results. Validity refers to whether the experiment actually measures what it is intended to measure. If the aim is to compare the heat of combustion of fuels, the method should control variables that would affect heat transfer, such as the mass of water, distance between flame and container, type of calorimeter, oxygen supply, and starting temperature. When discussing improvements, be specific. Use a lid to reduce heat loss and evaporation. Use a draft shield to reduce heat loss to air movement. Use a copper calorimeter instead of a glass beaker because copper conducts heat more effectively. Keep the flame to container distance constant. Stir the water to distribute heat evenly. Repeat trials to improve reliability. Use a more insulated calorimeter to reduce energy loss to the surroundings. Each improvement should be linked to the quality of the data. Now let's slow the episode into a simple exam pattern. If you are given a thermochemistry question, first identify what is being asked. Is it asking for energy absorbed by water? Is it asking for heat of combustion per gram? Is it asking for heat of combustion per mole? Is it asking for the sign of delta H? Is it asking for an evaluation of the method? Then collect the data. Mass, temperature change, specific heat capacity, calibration factor, mass of fuel burned, molar mass. Then choose the equation. Q equals mc delta T, or Q equals calibration factor times delta T. Then calculate carefully. Convert joules to kilojoules if needed. Convert grams to moles if needed. Check the sign. For combustion, energy is released, so the enthalpy change is negative. Then write a sentence that explains the result. Do not leave the answer as a lonely number. Say what the number means. For example, the reaction released a certain number of kilojoules of energy per mole of fuel combusted under the experimental conditions. Then, if asked, evaluate the limitations. The main limitation in simple calorimetry is usually that not all energy released by the reaction is transferred to the water or measured system. This leads to a calculated value that is less exothermic than the accepted value. That means the magnitude of delta H appears too small. Now the laboratory is becoming quiet again. The spirit burner has been capped. The thermometer has settled. The water is cooling gently back toward room temperature. The graph paper lies on the bench with a neat energy profile drawn in pencil. The reactants are labeled. The products are labeled. The arrow shows energy being released, and the equation beside it carries the small but important symbol delta H. Tonight, you have seen that chemical reactions are also energy stories. Exothermic reactions release energy. Endothermic reactions absorb energy. Thermochemical equations connect balanced chemical equations to enthalpy changes. Calorimetry allows energy transfers to be measured. The equation Q equals mc delta T helps calculate heat absorbed or released. Calibration factors account for the energy change of the calorimeter system, and careful evaluation helps explain why experimental values can differ from accepted values. So, as you rest now, keep the idea calm and simple. A fuel burns, water warms, a temperature rises, energy is calculated, a reaction is described, and chemistry becomes not only the study of substances, but also the study of the energy moving quietly between them. This has been Sleepy Steve. Sleep well, and let the warmth of thermochemistry settle gently in your mind.